We did our combinations notes out of our textbook. We also have these additional notes, so some of this is going to be review. The key thing in a combination is now we have to decide when we read a question, does the order matter or not? If the order doesn't matter, it's going to be a combinations question. And different than permutations, where permutations you almost never use the formula, because you can use spaces for decisions and choices instead. We use the formula a lot in combinations. And that line should be. So the formula NCR is really just your permutations formula with the order divided out. So you take the permutation, divide out the order, and you have a combination. So some special cases, if you have n things and you choose all of them, and the order doesn't matter, that would be one way to do this. Eddie, you can come pick up one of each of these 6 things. If you have n items and you choose one of them, there are n ways to do that. And here is the formula explanation why 52 choose 51 is exactly the same as 52 choose 1. So 52 choose 51. Every time you're making groups where the order doesn't matter, whatever size you started with, when you make a group of 1, you're left with a group of 51. And this happens all the way through. Laura, did you grab one of each of those 6? I'll re-explain the final project once we're done our notes for today. So for example, choosing 6 items from 10, making a group of 6 will automatically leave a group of 4, right? And then making a new group of 6 will make a new group of 4. So choosing groups of different sizes, and then we saw that you could now solve questions like this. If x does not equal 7, and 13 choose 7 equals 13 choose x, what's x? And the simple answer to this is that these two numbers have to add up to 13. And so x would equal 6. Oh, see what I did there? Okay. So one of the fun things that we can figure out in combination questions is a very popular game called poker. Poker, you get 5 cards, right? You want to play against someone who thinks the order matters. They're like, oh, I got 10 Jack, Queen, Ace, King dealt to me. I was so close to getting a straight, but the order was off. Well, no. When you're playing poker, it doesn't matter the order you get the cards in. You can rearrange them in your hand. So you would still have 10 Jack, Queen, King, Ace. You would still have a straight, even if it wasn't dealt in that order. So order doesn't matter, and the number of poker hands. 52 choose 5. We're going to go to our calculator and figure this out. Speaking of calculators, did anybody forget their rental calculator here on Wednesday? I can find it out by scanning the back, but Almost 2.6 million. 2,598,960. Which is maybe one of the reasons that playing the game has intrigue, because you can play it a long time and never get the same hand again. So for example, I'm going to take random 1, 2, 3, 4, 5. Let's see what poker hand I got. I got 6 of hearts, 9 of hearts, 7 of clubs, 2 of diamonds, and 2 of clubs. Take a long look at this. You will probably never, ever, ever see this again for the rest of your life. Because what just happened is I just pulled out this hand. And the chances of getting this exact hand are 1 in 2.6 million. But how is this hand? Kind of sucks, doesn't it? I mean, I got a pair, but they happen to be a pair of 2s. So if anybody else gets a pair, they're going to beat me. So this wasn't a really good hand, but the chances of me getting this exact hand were just as likely as getting a royal flush in spades. 1 in 2.6 million. But this is considered, obviously, worse than getting the royal flush in spades, right? Had I got the royal flush in spades, I probably would have just canceled class right now. I know. It would have been so much more exciting, right? So 1 in 2.6 million. A committee of 2 boys and 3 girls is to be selected from a class of 15 boys and 18 girls. How many ways can this be done? And this is I was going to say a combination, which is the right word, but I don't want to use it because we're doing combinations. This is a bit of our spaces and decisions, ideas that we learned in permutations, mixed with combinations. Because we have 2 main decisions to make. We have to decide which boys are going to be on there, and we have to decide which girls are going to be on there. And how many choices do we have for boys? Well, there's 15 boys. We need to choose 2 of them because the order does not matter. It's a committee. When you have a committee of 5 people, the order they were chosen doesn't matter. They get to be mixed up once they're there anyways, right? If I gave you groups to do group work, and I put you guys in a group, and then afterwards you're like, I want a new group. And I'm like, okay, I'll just give you the same group in a different order. You'd be like, no, that's the same group. For the girls, there's 18 girls. I need to choose 3 of them. And because this are the 2 decisions, I need to multiply between them. So 15 choose 2 times 18 choose 3. And just a reminder, the choose formulas are really easy to remember to change them without even looking at your formula sheet. 15 choose 2 will have a 15 factorial and a 2 factorial, and the other number has to add up. So the bottom 2 numbers add up to the top. So 18 choose 3 is 18 factorial. It would have a 3 factorial, and the other number would be a 15 factorial. So one of the things you might notice on a multiple choice question is the multiple choice question had this as the final answer. And it looks really weird. Because what did they do? They're like, hey, those 15 factorials would simplify. There's 6 pages over there you need to pick up. 1, 2, 3, 4, 5, 6 packages. Okay. A group of students must be separated into 3 smaller groups. Group A has 8 students, Group B 5 students, Group C 7 students. How many ways can this be done? Yeah, all 1 of each. Yeah. 1, 2, 3, 4, 5, 6. Okay? One of the things in this question to be careful with, can you see yourself getting confused by seeing the word group and thinking grouping strategy? This is not a grouping strategy. We're making groups. Does order matter in groups? No. Do we have more than one decision to make? Yes. We have to choose who's in group A, who's in group B, and who's in group C. 3 decisions. There's 20 students in total. Does that make sense? If you choose group A first, you have 20 people. You could choose any 8 of them to be in group A. Next decision is group B. Why is group B not 20 choose 5? 8 of them are already in A. So if we make the decision of B second, now there's only 12 students left. And we need to choose 5 of them for group B, right? And there you are sitting in class, you're a part of the 20, you weren't chosen for group A, you weren't chosen for group B, and you're wondering, I wonder what group I'm going to be in. Well, hopefully you're not wondering that before the teacher tells you, because for group C now, how many people are left? There's 7 people left, and we need to choose all 7 of them. And of course, 7 choose 7. Well, that's equal to 1, because obviously, if you're the one of the 7 people that's left, I hope you figured out you're going to be in group C. Now, it's interesting because it would not have mattered if I would have chosen this in a different order. So if I chose group C first, this would be 20 choose 7. And then group A, now there's 13 left, I have to choose 8 of them, and 5 choose 5. The numbers look completely different, but the answers will be the same. And I can show you why they'll be the same if we just play around with our formula. So 20 factorial would have 8 factorial and 12 factorial, and 12 choose 5 would have a 12 factorial and a 5 factorial and a 7 factorial. And I'm just going to write 1 for 7 choose 7. But no, I'm going to lift the formula because it's cool. In the formula, had you used the formula, it does remind us of something. What's the other number that adds up? 0. So this is a good reminder that 0 factorial is equal to 1. And one of the reasons that 0 factorial is defined to be equal to 1 is not that it means anything that we can use, but it makes our formulas work in all situations. So we need 0 factorial to equal 1 in order for our formulas to work. And the second one, right, with different numbers, you're like, how come this is the same? And then 13 choose 8 would be 13 factorial, and 8 factorial, and 5 factorial, and then, of course, now if I go through here, in the first one, I would notice my 12 factorials would cancel out. Obviously, all of this is 1. And so it simplifies to 20 factorial, 8 factorial, 5 factorial, 7 factorial. And the next one, if I go and simplify things, sure enough, the 13 factorials cancel out. And of course, this is equal to 1. And I have 20 factorial over 7 factorial, 8 factorial, 5 factorial. Identical answers. So I just wanted to show that the order doesn't matter. But then another student said, well, I did this question in a completely different way. I decided to line up the students from shortest to tallest, all 20 of them, and then I took a hat and I cut out 8 letter A's out of paper, 5 letter B's, and 7 letter C's. And I just let them pick out of the hat. And every different way of ordering those letters would be a different group. And all of a sudden they said this, I thought of it as a Mississippi question. If I order the students from shortest to tallest, and I took 8 letter A's, 5 letter B's, and 7 letter C's and thought of it as a Mississippi question, well, normally that would be 20 factorial because all the letters are different. But there's 8 A's, 5 B's, and 7 C's, and I get the same answer that way as well. Which makes combinations and permutations an interesting kind of unit. Because we've developed a bunch of different strategies, and sometimes 2 completely different ways of thinking about something can get you the right answer. Unfortunately, there's lots of completely different ways you can think about things that get you the wrong answer as well. So that can be a little bit frustrating, because you're like, I think my brain says this makes sense, but then someone points out an error in your logic. And we're going to do that in a second. But first we'll do this question. Find the number of poker hands without any clubs. Okay? So if I want to deal 5 cards, 1, 2, 3, 4, 5. Did I get no clubs? Diamonds. Spade. This is good. Diamonds. This could read. Oh, I got clubs. Okay? In order to make sure, right, if I wanted to guarantee that I give you no clubs, does it make sense that if I like secretly take out the 13 clubs beforehand and then like give you 5 cards, I'm like, did you get any clubs? You'd be like, no. I'm like, that's amazing. Right? So if we take the clubs out, leaving you with only 39 cards, and then you choose 5 of them, this would be the number of ways of getting a poker hand with no clubs. Okay, 39. And it's a really pretty answer. I know what you're thinking, it could have been prettier. One number different. But 5, 7, 5, 7, 5, 7. So, really quite symmetrical, quite cool. So there's 575,757 poker hands without any clubs. Because poker hands have 5 cards. And so now I'm going to have a little bit of fun. I am going to, I know I'm a math teacher, but secretly I've always wanted to be a salesperson and sell things, right? And I think I could sell like things you don't need. I could convince you, yes, I need to buy that. So I'm going to practice my salesperson skills here. I am going to sell to you 3 different ways to logically solve this problem. And you have to decide which salesperson you should believe and which one you should not. Because the salesperson is going to try to say, this is the perfect way to solve this question. This makes complete logical sense. This is how you should think. Okay? And now, depending on your level of trust of me, right? Some of you trust me completely, you shouldn't. But you might feel that all 3 are right. Because that Mr. JR would not ever teach us something wrong. Right? Some of you don't trust me at all. You're like, all 3 of them are probably wrong. And then after we go through this exercise, he's going to go, haha, I'll show you the right way to do it. Or maybe a mix. Maybe 1's right, maybe 2's right. We'll have to find out. So here we go. Method number 1. The first correct way to do this. I want poker hands with at least 1 club. Well, I'm going to take out my 13 clubs. There we go. And if I take out all 13 of them, and from those 13 cards, I choose one of them put it aside. I already have a club in my hand, and it could be any one of the 13. I then take those other 12 cards, I mix them back up in the deck, and I pick 4 more. Could I get another club? Absolutely. Could I get no more clubs? Absolutely. Will I have at least 1 club in my hand? Yes. So 13 choose 1. I now put the other 12 cards back in. There's only 51 cards left because obviously I took out 1 club. And I'm going to choose 4 more. And I have a poker hand with at least 1 club. 4 more. Method 2. I'm going to use the knot strategy. This seems like a perfect place to do that. The total number of poker hands is 52, choose 5. And in part A, I figured out the number of poker hands with no clubs. Those ones would be bad. So if I subtract those bad ones, 39, choose 5, all minus the bad, I should be left with all the poker hands with at least 1 poker hand. And this must be right, because why would I show you that in part A and have this as part B, unless there was some sort of connection? So this strategy also must work, just like method 1.
I don't know how good of a salesman you are, but you really are good at making me question everything.
This is part of the plan too. Method 3. Another strategy that we learned in permutations that can also be applied to combinations is cases. So we look at things separately. We look at case 1, and there's going to be a lot of cases here, so this strategy, although it works, is kind of annoying. Is case 1, we're going to count the poker hands with 1 club. That means I have 13 clubs, I choose 1 of them, and then from the other 39 cards, I choose 4 more. That's guaranteed to have 1 club and only 1 club, because I chose 1 club from the 13, and then from the other 39 cards, I chose 4 more. So this is going to be pretty repetitive here. Because at least 1 club, case 2 would be 2 clubs. So same strategy, I have 13 clubs, I choose 2 of them, and then from the other 39, I choose 3 more. Case 3, 3 clubs. And you can see the repetitiveness in this one. And although this, like the first 2, is also correct, as a salesperson, I find it harder to sell this one just because it's longer, even though it's right. So, 13, choose 3. 39, choose 2. Case 4, 4 clubs. 13, choose 4 of them. 39, choose 1. And finally, case 5, all 5 clubs. 13, not 39. And whatever answers I would get for each of these 5 different cases, I'd add them up, and the total would be the number of poker hands with at least 1 club. Yeah, now as a real salesperson, if I decided on a job, I probably wouldn't approach the person and say, just so you know, I might be lying to you. Right? That's usually not a good salesperson pitch. I just sell it right away that this is the right way to do things. Okay. How did I do? You like them all? No, because this has got to be a trick in here. Are they all bad? Okay, so now, I just want you to, you can vote for all three. You can vote for none of them. Okay? If you like a method, you're going to put up your hand. Does my brain work that way? Does method 1, my brain like that? Does method 2, my brain like that? Does method 3, does my brain like that? Okay? So make your decision how many you like. You can like more than one. And just, if you like a method, put up a hand. Are we ready? Starting from the back. Method 3, how many people like method 3? Okay. Method 2, how many people like method 2? Okay. All right. Method 1, how many people like method 1? All right. Now, if we wanted to analyze this, we could actually figure out these numbers. If all three numbers are the same, that would either mean they're all three right or they're all three wrong. Correct? At least that would break things down for us. So I'm gonna take out my calculator here and put out some numbers. This one is 3, 2, 4, 8, 7, 0, 0. And then this one is 2, 0, 2, 3, 2, 0, 3. And this one is 2, 0, 2, 3, 2, 0, 3. Okay, interesting. They can't all be right. They could still all be wrong. So we've just canceled one thing out. We know they all can't be right. One of these three, or two of these three, or all three of these three may still be wrong. Yes.
I mean, method 1 is saying there's more hands without the clubs than there are with the whole deck.
Okay. This seems bad because the total. Oh, is that number right? Did I just.
Yeah.
Woo! That's scary. Okay. There are 2.6 million poker hands in total, of which 3.2 million have at least one club. Something seems wrong, right? It's like those fraction. Have you seen those shirts people wear that there are 3 types of people in the world? Those that get statistics and those that don't. Seen jokes like that where things don't, right? 4 out of 3 students have trouble with math. Things that, like, something's wrong with this number. Okay, so this one has to be bad. And we have to figure out, like, I like that one. Doesn't that seem an easy way to do things? I choose one club, guarantees that I have one club, put the other ones in, I could get more clubs. What's the problem? Why did that one come up as too much? I will tell you, these two work. The all minus bad is probably the best strategy here because it's a lot less than the cases. But the cases method sure looks a lot like method 1. What went wrong in method 1? Well, let's analyze method 1 just a little bit. Move that number. No, that didn't move it up. There we go. Let's move these up so give me some space. So in method 1, 13 choose 1, I could have chosen the 5 of clubs, right? And then I put the other 4 cards back in the deck, I mix them up, and I might have chose the King of Hearts, the 7 of Diamonds, the 3 of Clubs, and the 2 of spades. That's a possibility. A second possibility could be this. In the 13 choose 1, I could have chosen the 3 of clubs. And then got the king of hearts, the 7 of diamonds, the 2 of spades, and what am I going to write in the other one? That's going to point out why this is bad. I could have got the 5 of clubs. And in this method, it would have counted those 2 poker hands as different. But in fact, they're the same. Okay? Pretty easy to disguise things, but I counted over 1.2 million hands the same. That's like a little bit of an overcount. Just a bit. Right? Can you imagine you're working at the grocery store? Someone brings in 5 apples, and you write down 1.2 million and 5 apples and charge them. They'd be like, why is my bill so much? Oh, I'm sorry. I just overcounted your apples by 1.2 million. Just a simple mistake. Easy to do. Right? So in permutations and combinations, it is easy to overcount. Okay? How did we overcount and what's the issue? Well, what comes up here is that we were counting something where order doesn't matter. Technically, anytime you make 2 different decisions, you are adding a permutation strategy which adds some order. It doesn't matter in the cases question because your decisions don't overlap. Here we're choosing clubs, here we're choosing not clubs. But here, there is something that can be chosen in the first decision that can also be chosen in the second decision, creating this order problem. As long as you're doing decisions like in the boys and girls when we decided, there was no overlap there. So we don't have an issue of counting somebody twice. This one, the club, could go into both spaces. And so that creates a problem. So when you're doing combinations questions and you're adding decisions, we have to just make sure that that order doesn't overlap. When we get back from the break, we are going to begin class with an analysis of poker hands. Why is it that 3 of a kind is better than, well, something obvious. Your brain says, well, 3 of a kind obviously should be harder to get than 2 of a kind. But why is it that 3 of a kind is better than 2 pairs? That one always was what, like when I started playing poker, I was like always like, how do I remember that 3 of a kind is better than 2 pairs? Because it makes sense that 3 is harder to get than 2, but 2 pairs takes 4 cards to do that. Well, 3 of a kind only needs 3 cards to do that. Why is it better? How much better is it? And how does that help me play poker and understand the probability and choices behind it? So that'll be something that we'll do after we get back from the break.